we'll get to chat a lot more.
It's my pleasure to introduce Pedro Domingos for this distinguished lecture. Pedro is now a professor of computer science in University of Washington, and he's also the author of the book, The Master Algorithm. He has won many awards, including, this book. If you want the signature afterwards, that you can.
Well, I have a copy. I have a Kindle version.
And he has won numerous awards, including the KDD Innovation Award, one of the highest honor in data science. He's also a fellow of Association for the Advance of Artificial Intelligence, received Fulbright Scholarship, Sloan Fellowship, the National Science Foundation Career Award, and he has numerous best papers. He has many influential work, for instance, in scaling out some of the machine learning algorithms and how to do inference maximization, social network, and he has some work on unifying logic and probability, and then deep learning. He's going to talk to us on deep learning today, and it is an exciting new topic.
All right. Thank you all for being here. Can you hear me? Good. So what I'm going to talk about is sum product networks, which is a new type of deep model that we've developed at UW, and a bunch of people are now using and doing research on. This is joint work with my students and former students and postdocs, A. Friesen Loggins, Matthias Niepert, and Hoi-Fung Poon. Here's a roadmap. I will start with some motivation for some product networks. You know, why do we need them? What are they good for? And then I will describe what some product networks are and talk about different kinds of learning for some product networks. So I'll start with discriminative weight learning, followed by generative weight learning, and then structured learning. And then as time permits, I will discuss a few other things, applications, ideas arising from some product networks. So our overall goal in AI, and in this research in particular, is to build a brain. Right? We need a brain to control, for example, a self-driving car, or a home robot, or, for example, a website. Right? A website like Google or Facebook, you can think of it as, we need to have a big brain running that website, moment by moment, because human beings can't. Or a company. A company needs a brain, or a city. Right? A city has more and more sensors, all of these different infrastructure systems. We would like to intelligently control them continuously in real time. Or even a brain for a whole economy. Right? So this is the promise of AI. Now, of course, this is a very lofty and very hard and distant goal, but we know where to start. We need to start with the essentials. First of all, intelligence is all about having knowledge of the world, so we need a way to represent that knowledge. That's the first thing we usually do, is we pick a representation formalism for our knowledge, and then we need a way to learn that knowledge from data, because programming it manually would be hopeless, and then we need a way to do inference with that knowledge. Okay, typically, the inference is going to be intractable, and that's a big problem, and that's one of the things that we have to deal with. Now, as we do this, there's a certain number of desiderata that we want to keep in mind. They are, I think, fairly obvious. We want whatever system that does these things that we pick, we want it to be flexible, because flexibility is really what intelligence is all about. We need it to be robust, because if it's not robust, people in industry will never use it because it's not reliable. We want the inference to happen in real time. Right? You can't control a self-driving car or a home robot if you can't do inference in real time. So this is another very big constraint. And another very important one, particularly these days, is comprehensibility. If the system that we have is completely opaque, then that should make us very nervous. Right? We don't know when it's going to malfunction. We don't know how to debug it if it does malfunction. So this is another very important desideratum. So we would like to have these four things. And now, unfortunately, the two major kinds of deep learning that we have today, none of them actually satisfy all these desiderata. So the first kind, and this is the type of deep learning that is widespread in industry today, is what you might call function approximation. So function approximation is you have an input and it produces an output. Like you have an image and it says this is a cat or this is a dog. Okay? So convolutional neural networks, or convets for short, are a quintessential example of the function approximation type of learning. They have a number, so looking at those desiderata, in terms of flexibility, they are pretty bad. Right? So convnets are extremely inflexible. They have a fixed input, it has to be that image. They have a fixed output, it has to be one of those classes. So you basically have no freedom there. Also, they're not flexible because they require supervision for every data point. Right? This is a very stringent constraint that most of the time you can't meet. You need to assemble a data set composed of examples of these inputs and outputs. On the other hand, as a very strong plus, you can do real-time inference with coordinates, which is why the likes of Google and Facebook and Microsoft and so on like to use them. You know, you can deploy them, they will do inference in a fixed amount of time. They can be very heavy, and it might need a big data center to do this, but it's, you know, it's doable. They're also quite robust, right? Learning is hard, but once you have your ConvNet, and you know, deploying it and having it perform classification is actually something that's very, very robust. On the downside, they are highly incomprehensible. Okay, nobody really knows what's going on inside the ConvNet. It's a big pile of numbers. There's a lot of efforts to make them more comprehensible, but those are very much work in progress. So they need some of those, they need two of those Desiderata, but not the other two. Okay? Now, the other major type of deep learning that exists today is probability estimation. For example, things like deep Boltzmann machines, deep belief networks, and so on. Okay? Now, the advantage of this type of learning is that it's very flexible. So something like a deep Boltzmann machine, you can take any, you can ask it to infer any outputs from any inputs. It's a joint distribution over a set of variables, and I can use any of those variables as the evidence and any other set of variables as the clue. So it's much, much more flexible than things like coordinates. Also, it's very flexible because it doesn't need supervision. If you have some supervision, you can use it. If you have none, that's okay. If you have supervision, you can also write. So you can do the full spectrum. So in terms of flexibility, these models score very high. In terms of efficiency, however, they're terrible. So the inference in these models is very straightforward. The inference in these models is anything but straightforward. Inference in something like the Boltzmann machine is worse than NP complete. It's sharp P complete. Okay? As a result of which you have to do it approximately, and then life becomes very, very hard. It's not reliable. It doesn't take a predictable amount of time. You don't know if the results will be accurate or not. So it's also not very robust. And it's just as incomprehensible as ConvNets. Okay. So this is the state of the art. What I would like to propose here is a new class of deep learners that actually does both of those things. So it does both function approximation and probability estimation. And it satisfies in each of those cases all four Desiderata. So it actually, you know, combines the best of both worlds and goes a little bit beyond that. And in fact, as far as the complexity of inference goes, some product networks actually do something that was previously assumed to be impossible, which is to have a quite expressive class of models where the inference is always tractable. So we have a lot of flexibility combined with still very efficient real-time inference. And this work has been recognized with a number of best paper awards at top conferences like NIPS, UAI, and WHCAT. So, what are some product networks? Maybe a good way to build towards some product networks is to start from graphical models, which is what deep architectures like deep Boltzmann machines are an example of. But of course, things like Bayesian networks are examples of graphical models, and so are Markov random fields, and so on. And what is a graphical model? A graphical model is just a representation of the joint distribution of a set of variables. And it has the advantage that it's very compact, much more compact than listing the probability of all the exponential number of states. Okay? The problem, however, is that the inference in general can be intractable. So for example, here's a very classic and simple Bayesian network. Two different things could cause the alarm at my house to go off. It could be a burglary, it could also be an earthquake. If I want to compute what is the probability that there's a burglary given that the alarm went off, right? I need to get rid of this earthquake variable. I need to sum it out. I need to marginalize it. And in general, the cost of my inference is going to be exponential in the number of these so-called hidden variables. Worst case, it's not exponential in all the variables. This one is something called the true width of the graph, but the bottom line is, this is not going to be feasible. The true width, for example, of an image is the height of the image. Okay? So the inference is going to be exponential in the height of the image. So this is not computationally feasible. Okay? As a result of which, we need to try something else, like approximate inference with significant problems. So the inference is hard enough, but now the learning problem, which is the main one that's going to interest here, is also hard. Why is the learning problem also hard? Well, the general idea there are, of course, countless algorithms for learning these kinds of models, but generally what they do is the following. They take the empirical statistics of the data, like how often different things occur and the means and variances of different variables, and what they do is they learn the model parameters, the weights on the network, for example, such that the predicted statistics according to the network match the empirical statistics. Okay? We want to treat the parameters until the predicted and the empirical statistics are the same. Okay? Now the problem is that this is easy, but to compute the predicted statistics, you need to do inference in the model. And the inference, as we just saw, is intractable, so we need to do approximate inference. And now the approximate inference is unreliable, meaning it can give very noisy or even just plain wrong results. And when you combine that with the fact that there's usually no closed form solution, and when there are hidden variables, there isn't even a global optimum. There are many local optima, so you don't necessarily converge to a global optimum. The interaction of the non-convex learning and the approximate inference can just makes life very, very hard. It can be shown both theoretically that this can give arbitrary bad results, and empirically we know that it makes life very hard. So, for example, people in things like equal to machines, you have to do approximate inference using something like gift sampling, and then when you do something like contrastive divergence, because just doing maximum likelihood is intractable, then it tends to not work. And even if you can make it work, it's very brittle. Okay? Surely there must be a better way. Okay? Yes, we want these powerful models, but we don't want our life to be infernal like this. So what can we do? Well, this is where some product networks come in. Maybe one way to introduce them is to think of it in terms of a Venn diagram. So let's say that this slide, this white rectangle, is the set of all probability distributions. And now we're interested in representing probability distributions compactly. So graphical models allow a certain subset of all probability distributions to be represented compactly, but not all. Okay? Most distributions can be represented compactly, but we don't care because we're never going to meet them in real life anyway. Okay? Now, some product networks have a different subset of distributions that they can represent compactly. That subset has an intersection with a subset that can be represented compactly using graphical models. Right? So things like, for example, hidden Markov models, mixture models, low-truth models, they are in this intersection. Okay? They can be represented compactly as both graphical models and some product networks. And there are also some actually previously not known classes of tractable models that are still in the intersection, so that's an interesting point. But now the big difference, so in terms of representation compactness, it's so what, right? Sometimes graphical models are better, sometimes some product networks are better. The big difference between them is in the cost of inference. Because the cost of inference in graphical models is generally exponential, whereas the cost of inference in some product networks is always linear. Whatever some product network you have built, you can guarantee that answering any marginal or MAP query in that some product network is only going to take time at most linear in the size of the network. Right, so this is just spectacularly better than what we can do with graphical models. And we're going to, of course, see how this all comes about. Okay? So, what is a sum product network? A sum product network is defined recursively, and the definition is very simple. In fact, it's kind of interesting why people didn't come up with this 50 years ago, but apparently they did. So, it's a recursive definition, and here's the base case. A univariate distribution is a sum product network. Okay? So if you have a discrete variable, maybe you can have a multinomial distribution. Here's the variable x. If it's continuous, it can be modeled by a Gaussian, the usual things. Okay? So these are going to be the building blocks of some product networks. The next rule is that a product of some product networks over disjoint variables is a sum product network. Okay? The variables have to be disjoint. So I can have a product here between a sum product network over one set of variables and another sum product network over a different set of variables. This is okay provided that there is no common variable between these two. Okay? So here's my variable x with one multinomial distribution and my variable y with another. This so far is not very interesting. All I'm really doing here is forming the joint distribution of x and y as being the product of independent distributions over x and y. Okay? The next one is a bit more interesting. It says that a weighted sum of SPNs over the same variables is an SPN. Okay? So now we can actually have these two SPNs over the same variables, and now I can do a weighted sum of them, and that is still an SPN. Okay? And what we've actually done here is, again, not a surprising thing. This is just a mixture model. Okay, these are the mixture components, and these are the mixture priors. Okay? And so every time you see a sum node in a sum product network, you can think of it as being a mixture variable. Right? It's a hidden variable that I sum over. Okay? Why is, and this is it. These three rules are all that goes into making a sum product network. The reason this is powerful is that you can recurse. You can do any number, any alternation, any composition of these things. You can have a network with many, many, many layers of sums and products. And remember, every layer of sums is another layer of hidden variables. So if you have 100 layers of sums, you have a model, you have a hidden architecture that is 100 layers deep. Okay? And as we'll see, you can train things that deep and deeper with no great difficulty. Okay? Notice also that this is a DAG, right? It's not just a tree. Right? You can have, here's a bank of distributions over x5. Like, let's say they're different multinomials. This distribution over x5 gets used here and here, and those in turn gets used, over there and over there, right? So this can be a very complicated, very rich graph of connections. Okay? Provided we obey those three rules, this is still a valid sum product network. Okay? So that's what a sum product network is. Now, I made the claim that all marginals in a sum product network could be computed in linear time. This is what seems to be a miracle, right? Now, how can you have a model that's this rich, and yet the inference is always not only tractable, in fact, linear time? Well, here's how it happens, and it's hopefully not hard to see why the inference is tractable. So let's see, here's a very simple sum product network over variables x and y, and let's say that I want to compute the probability that x is equal to 0. X has two values, 0, 1, and 2, and I want the probability that it's 0. In order to compute that, I need to sum out y, right? That's what I need to do, right? The probability that x equals 0 is the probability that x equals 0 and y equals 0, plus the probability that x equals 0 and y equals 1, plus the probability that x equals 0 and y equals 2. Okay? And in general, of course, this would be an exponential blow-up in the number of the y variables. Okay? So how do we do this? It's very simple. The evidence variables, in this case x, I just take their probability. So this is the probability in this branch that x equals 0. This is the probability in this branch that x equals 0. As you see, it's a little bit small. The variables that I need to marginalize over, I just marginalize over at the leaves. Right? So if the distributions are normalized, it's actually just going to be 1. It's the sum of these 3 is 1. And the sum of these 3 is 1. And then what I do is I do a bottom-up pass through the network, computing at each product node the product of its children, and each sum node the sum of its children. And then what I get at the root is the marginal probability of x. It's 0.26 in this case. Okay. Now, why is this possible? The reason this is possible is actually very simple, is that addition is commutative, and multiplication is distributive over addition. Okay? So what happens is that the big sum that I have to make over all states, I can, so I have the sum over all states of this network. This network is a sum over these components, right? Because addition is commutative, I can switch the order of those sums. So I can make this be the sum over this sum over these children of the sum over states. Right? So I can push the outer sum that's marginalizing past sum nodes with no change in size. Okay? Now what happens at a product node? At a product node, provided that these nodes are disjoint, I can apply distributivity. And I can push the sum past the product. And then something very important happens is that whereas before I was summing over the joint states over the variables, after I push it through the product, I'm only summing over the products, over the states of each of the component subsets of variables. So whereas before I would have, if this had n variables, whereas before what I had was cost n squared, now the cost is just 2n because it's n, and then I do a sum of n things, and I multiply it by another sum of n things. Okay. So as I push the sum past the products, the cost gets lower and lower and lower, until finally, of course, I'm just doing the sum over a single variable, in which I can do in essentially O of 1 time. Okay. So this is why computing marginals is efficient. Computing MEP states is also efficient. In most problems, what you actually want to do is compute the most probable state of the query variables given the normals. Like, for example, the Viterbi algorithm, and by the way, HMMs, as I mentioned, they are a special case of SPN, so Viterbi is a special case of this inference, right? What you want to do is you want to infer, like, what are the words that were spoken given the sounds that I just, had, right? We can also do that in linear time in the following way. Step one, I replace all the sums by maxes, okay? So here, at the leaves, instead of summing out the hidden variables, I just take their mode, okay, the probability of the mode, and then, every product does the product, every product node does the product of its children, and then every max node takes the maximum of its children, okay? And what this gives me at the root is the probability of the most likely state. But now what I actually want is the values of the values in the most likely state. And for that, I have to do what's called the traceback phase. Again, if you know Viterbi, Viterbi is a special case of this, where at each max node, I pick the maximum valued child, okay? And what that does is it retrieves a subtree of the data, okay? You can think of this as having parsed the input. Again, PCFGs are another special case of some product networks, okay? And then the variables that I read, the variable values, for example, here, right? Finally, I chose this branch, and the mode of y is this value 1, so this is what the value of y is going to be, okay? So marginals, 1 pass, MEP states 2 passes, and I'm done, okay? So the inference is linear, meaning we're going to be able to do this even for very large networks, in a fraction of a second, and with complete reliability. There's no approximation. It's exact inference. Now you may be thinking, okay, this is all very nice, but what do some product networks actually mean, right? Is this just a nice trick that we found to make inference efficient? Like a lot of the appeal of graphical models is that there's a natural match between the graphical model and your intuitions about the world and how variables, interact with each other and so on. Is there a similar intuition from some product networks? Actually, there is, very much so. The basic, and it's a very different one from the one in graphical models, but one that is very well matched to a lot of problems like vision and language and so on. And the basic idea is the following. We already saw that sums correspond to mixture models. So a sum node is really a clustering of the subspace, right? Each node is over a subspace of the variables, right? A sum node represents a clustering of the instances in that subspace. A product node is a feature, right? A feature is a conjunction of things, but the probabilistic version of that is a product of the corresponding distributions. So what happens in the sum product network is we have this alternation between forming features and then forming clusters that use those features, and then forming bigger features that use those clusters as features and so on. Okay? So for example, let's say you want to build a probability distribution over images from a corpus of images. And you might learn a sum product network as follows. Like the top node is a sum node. It says, you could be either an indoor scene or an outdoor scene. And if in your corpus 80% of the scenes are indoors, the weight of the outdoor component will be 0.8. Okay? And then maybe the outdoor scenes could be countryside or city. So here's a snippet of the network from the middle. This is city. So, but now a city scene, right, now can be decomposed into different things. There's the sky, there's the buildings, there's the people in the cars, there's the roadway, right? So now we have a product over those things that the scene decomposes into, okay? Now each of those things in turn is going to have a sum, like, well, what I have here, could be different things. Could be a car, could be a person riding a car. I have a distribution over those. And then if it's a person riding a bike taxi, for example, that in turn can decompose into person and bike taxi and so on and so forth, all the way down to individual pixels. Okay? So some of the SPN models that we built for images are literally models that go all the way from individual pictures to the pixels to the whole image. Okay? And in fact, we can make this intuition formal and define a representation language such that if you write your model or learn your model in that language, the inference is always guaranteed to be tractable. So we call it tractable Markov logic because it's a subset of Markov logic, and it's a tractable subset of Markov logic. In essence, what you have in tractable Markov logic is 3 types of statements. There are subclass statements, like, for example, family is a subclass of social unit. There are subpart statements, like, for example, a family has 2 adults and maybe some number of children. And then there are relation statements, like, for example, in a family, the adults are parents of the children, and, for example, here's a concrete fact, Avery and Jesse are married. Okay? So as long as you express your knowledge in this form, we can compile your knowledge base into a sum product network of the same size, and so there's no blow up, and then the inference is very fast. And in particular, we've actually used this to build a very big knowledge base from the web by agglomerating information from DDP and Freebase and Nell and whatnot. So that the knowledge base that we have has millions of objects and billions of parameters, and you can answer arbitrary questions, arbitrary conditional queries in a fraction of a second. So you can actually do that at interactive speed, okay, over a knowledge base of this size, and the answers are completely reliable. A lot of, as I mentioned earlier, a lot of the traditional tractable models are clean, special cases of sum product networks, things like hierarchical mixture models, thin junction trees, which in particular include hidden Markov models, probabilistic context-free grammars. What I'm describing here just includes non-recursive, but SPNs have been extended to include the recursive case as well. And in each of these cases, there's not only does the special, the SPN has these as special cases, but it also extends them in significant ways. So, for example, thin junction trees are SPNs, but most SPNs as junction trees are a complete clique. So if you look at the distribution model by the SPN and try to model with a graphical model, it's one big clique, so it seems completely intractable, and yet it isn't. Or for example, PCFGs are models of sequences, and you can only divide a sequence of variables into two contiguous subsequences. In an SPN, you can divide a set of variables in an arbitrary way. Okay? And that's only one of several ways in which SPNs are more general than PCFGs. Okay, so that's the representation. You can represent some models compactly, not all, but including some models that can be represented compactly as graphical models. The inference is always tractable. This is the big advantage. We also saw that it's, it allows you to build up your knowledge and interpret the network in a fairly straightforward way. So unlike things like convex and the default machine, you can go to each node of a sum product network and understand what it's saying. It's like you have a model over faces. There will be a node that there's models of noses. And then you look at the different components and you're like, oh, this is cluster A of noses, cluster B of noses, cluster C of noses. Okay, and the same thing for eyes and faces and so on. So, but now let's see how we learn them. Let's start with discriminative. So first of all, let's assume that the architecture is given, as is typically the case in deep learning, and we're just trying to learn the weights. And now there's, you can learn the discriminative or generative. And then, then we'll look at how actually we learn the structure of the sum product network. So discriminative sum product networks, the goal here is to predict some variable or variables given others when you know a priori which variables are going to be evidence and which variables are going to be clues. Okay? In particular, if you're familiar with conditional random fields, sum product networks are solving the same problem as conditional random fields, except that the inference is going to be tractable. Okay? So this could be a whole set of variables that you're trying to predict. Why? Or it might just be one single class variable. So for example, we could do object recognition, and we'll see that in a second, using this set. So X is a bunch of features of the image. Y is whether the image is a bird or a dog or whatever. Okay? And the hidden variables, of course, correspond to the sum nodes. Notice that I don't have to start from the raw pixels. I can, and in some cases we do. You can compute any features of the image that you want. And again, as in conditional random fields, because we're just doing conditional modeling, we don't have to worry about the interactions of those features. So we can just be absolutely anything that we want, which makes it very powerful. So how do we do this? Same as in CRFs. We're going to learn by maximizing the conditional log likelihood of Y, the output, given X, the input. Okay? So this is, so we need to compute the gradient of the conditional log likelihood. So the conditional log likelihood, so the likelihood is P of Y over X, which is the same as P of YX over P of X, right? And the log of a ratio is the difference of the logs, right? So this is what you wind up with. It's actually quite intuitive. Is the gradient, the gradient of the log conditional likelihood is going to be the difference between The probability is that you compute when you know the correct labels, when you know the y's, so you're only summing over the hidden variables, right? Those are always hidden, so always have to sum over. And what you compute when the classes are also unknown. Okay? So what the learning, this is an instance of what I was describing earlier, what the learning is going to try to do is make these two things match. Okay? Now, of course, the problem in learning CRFs is that because both of these are the result of approximate inference, these are very noisy. And now your gradient signal is a difference of two very noisy things, and of course learning is going to be very hard. The big difference in SPNs is that these two things are both tractable, so we can compute them exactly, and now we actually have a high quality exact gradient signal, and the learning suddenly becomes much, much easier. Okay? And once we have this, of course, what do we do with the gradient? Well, surprise, we just do backpropagation. Right? In fact, backpropagation and SPNs are made for each other, because in SPNs, the functions that you have to backpropagate through are just sums and products, which are just the best behaved functions for differentiation that you can imagine, as opposed to sigmoids, which flatten out and use the gradient signal, or LUs, where the gradient pulls up and they're not even differentiable at the origin. None of those problems happen here. You're just differentiating through sums and products. Now, there is still one very big problem, which is the usual problem in deep learning, which is the problem of gradient diffusion, also known as the vanishing gradient problem. This is the reason deep learning didn't take off in the 80s, is that people couldn't figure out how to solve this problem. And the problem is that as you go down more and more layers, the gradient signal becomes fainter and fainter. It spreads out among all the different paths that you could take between the output and one of those weights, in the deeper layers, until you really don't know, who should be changed in response to what pairs. Okay? It's like, if you think of the gradient signal as, this as being like the mouth of a river, then the river starts to branch out into smaller and smaller tributaries until what you have is just, a very faint rainfall falling everywhere, and it's very hard to track. And we run into that problem in SPNs just as much as in any other deep model. So how can we solve it? Well, we can solve it by doing a very simple thing, which was already done in CRS, but there was no deep learning going on because that was just one layer. And the idea is to do hard inference. What do I mean by hard inference? Soft inference is what I just described. It's computing the margins, right? So the training should be done by comparing margins. But if instead of comparing margins, what we do is we compute the MAP states, right? So instead of having my signal be distributed among the children of a sum node, it all just goes to the highest valued child. Then I can go down any number of layers that I want, and the size of the signal is always the same. There is no gradient diffusion anymore. Okay? Another way to think of this is in terms of soft and hard EM. Right? In hard EM, we completely assign each example to a cluster. Like as in K-means clustering, we don't assign the examples fractionally. And, in clustering, that tends not to make a big difference, but here it does, because I'm going to go through many levels of this. So what does it mean to do learning of SPNs with hard inference? Well, we're going to approximate the gradient. The tilde here is because I'm going to be approximating my conditional likelihood, right? And so these probabilities that we saw before are sums, right, over all states of either y and h or just h, right? But what I'm going to do now is I'm going to approximate those sums by the single largest term in the sum, which is often a good approximation because these distributions tend to be very peaked, right? Especially as you conditional number information. There's usually a single dominant mode. Okay? So now what I'm going to do is I'm going to do that. So I'm going to do the MAP inference on this side over just the hidden variables, and on this side over the hidden variables and the classes. Okay? So I do two MAP inferences, and remember, what an MAP inference returns is a subtree of the graph. Right? You can think of it as a parse of the input. Okay? So here's the MAP inference that I get when I know the classes. Right? So in green, I picked up the subtree. Here's what happens when I don't know the classes. And now how do I learn? Well, what happens is that, remember, my learning signal is the difference of these two things. So if there is an edge that does not participate in either tree, then there's nothing to learn there, right? Because the difference is 0 minus 0. Okay? If there is an edge that is the same in both trees, again, there is nothing to learn because, I subtract this from this and the result is 0. Basically, if at a certain sum node I pick the right child, then I don't need to change anything. The learning happens when I pick the wrong child. So for example, here, I pick this guy, but over here I pick this guy. Okay? And this is what I want to do is like, what the gradient descent is going to do is like, I want to be less likely to pick this guy in the future and more likely to pick this guy. Okay? So again, the gradient, even in the hard case, has a fairly intuitive meaning. So that was for one example. Now, if you sum this over all the examples that are in your training data, what is the gradient that you get? Very simple. Your gradient signal is just the number of examples with the correct label minus the number of examples with the model guess. Okay? If the example, guess, if your model is good, then this will be the same as this, and there's nothing more to learn. Otherwise, the parameters need to change in order to make this number go up or down in order to match this number. Okay? So the learning is fairly intuitive, and now we can actually learn, with no gradient diffusion, networks with with tens or hundreds of labels, and maybe thousands, but we haven't, gone that far. Okay. So we tried this out on a standard, object recognition task using classic data set CFAR. It's like all labeled data, STL, a mix of labeled and much more unlabeled data, or maybe more unlabeled data. We did the standard Fisher extraction pipeline. In particular, we compile a dictionary of image patches and cluster them. This is all kind of like standard things that we just did the same as before. So the architecture that you'd expect, the lowest levels are logistic regressions, and then we alternate between sums and products until we get to the top level sum, which is over the classes of the objects. Pretty much the first thing you try for something like this. So what happened? The SPN beat all the other methods, including deep methods and things like SVMs and the Boltzmann machines, autoencoders, pooling, and so on and so forth. In particular, it's interesting to see how the accuracy varies with dictionary size. Right? So notice that the SPN is always ahead, but for example, compared to SVMs, which in the days before deep learning used to be the state of the art. Oops, and this just died. Used to be the state of the art for for object recognition. The SPN with 200 words in the dictionary is doing better than the SVM with 4,000, or about about the same. Okay? And this is because the SPN can construct these larger pieces of the image. So it can do, it can take small patches and dynamically compose them into larger patches. Whereas these other methods actually, they need to have the patches, or they need to have those larger patches because they're able to construct them. Oops. So what happened in STL? The idea in STL, and the reason this became a popular data set was this notion that you can make your supervised learning better if you pre-trained with unlabeled data, right? Do unsupervised pre-training, right? So we have only 5,000 labeled examples and 100,000 unlabeled ones. The thing that's remarkable here is that the SPN without unlabeled data did better than the other methods with labeled data. So it turns out that you didn't need to do unsupervised pre-training. As long as you had a better supervised learning, you could actually do just fine. Okay, what about generative learning, right? So in generative learning, what you want to do is you want to learn a joint model of all the variables. So for example, in the case of images, you don't just want to classify the image into cats and dogs and whatever. You want to have a model of how the world generates images. Okay? Well, the natural thing to use here, right, is some form of EM algorithm, right? EM is what people use to learn mixture models, and you can think of SPM as being an exponentially large mixture model, right? If you do all those distributions of products over sums, right, the number just keeps getting bigger and bigger until you have a sum over an exponentially large number of products. So in some sense, an SPN is just an exponentially large mixture model, and those sum nodes are hidden variables. So, so let's use EM, right? And we tried using soft EM. You have the analog here of the gradient diffusion problem. When you use soft EM, it doesn't really work because, it gets smaller and smaller fractions of examples propagating down until there's no learning signal. We do online learning, as is typical in deep learning, right? So, we present the instances one at a time and learn from those. And in essence, this is all that has to happen. Each SIM node maintains a count for each of its children. And then when I see an example, I do the MEP inference for that example. Okay, so I infer, the hidden variables, using, the MEP inference that we saw before, right? And this MEP inference picks out a winning child for each node, okay? And then, so we increment the count for the chosen child, okay? If a child wins an example, then its count goes up by 1. And then we renormalize to make sure the weights, still all add up to 1. You don't actually have to do this, because, the normalization, computing the partition function of an SPN is tractable, but the learning works better if you do. And then you just repeat this until you converge. Okay? So the algorithm is quite simple. It's really just, the form of YAM. But it's quite effective. And again, we haven't found a limit to the number of layers that we can learn this with. We evaluated this on a very hard problem, which is image completion. Image completion is like this. I'm going to give you a training set of images. You learn a model. And then I'm going to give you a test set of images where I hid half of the image. So your job is to fill in the missing half. Right? When you're just doing object recognition, when you're just classification, as long as you can find some features that are predicted, you're good. Image completion, you can't do without understanding the structure of the image at some level. Okay? So this is very, very hard. Most deep learning methods can't do anything close to it. So we use two data sets. Caltech 101 is a classic vision data set containing, a variety of objects. Olivetti is a set of faces. We compared with deep belief networks, deep Boltzmann machines, principal components analysis. Right? This is just a linear method, but for faces it's very good, right? It's what's behind eigenfaces. And also nearest neighbor. Right? So people in graphics call this problem the ink painting problem. And they found there that if you have a sufficiently large database, just using nearest neighbor to do the ink painting can work quite well. Meaning, I have a scene, I hide the block of the scene, I find the most similar scene in my database, and then I use the pieces of that scene to fill in the missing ones. Okay. So what happened? Well, to cut a long story short, the SPNs were easily the best of all these methods. We measured the mean squared error of reconstruction at the pixel level. So our measure of error is like the sum of all the pixels of the square difference between the predicted gray level and the actual gray level. The SPNs were better by a third compared to the best of these methods, and by even more compared to some of the others. But even more than that, the SPNs were orders of magnitude faster to learn and to execute than the DBNs and the DBMs. So for these guys, we had to do MCMC or belief propagation. We tried a bunch of stuff. It's all extremely slow. And even after all that slowness, the results are still, of very mixed quality. With SPNs, you just, basically get the results, at the push of a button. Okay. The learning is also a lot faster, partly because the inference is faster in cycle learning, but also because there are many fewer parameters to try. There's much less, like architecture engineering to do. Right? Usually in most papers you have to spend a lot of time getting your method to perform better than the, than the straw man. Our problem in this paper was getting the straw man to do anything useful, so the paper wouldn't look too unfairly favorable to us. So, so what happened? So here's the architecture that we used. We start out with a mixture model for each pixel. We model each pixel with a mixture of Gaussians, and then what we do is we build things up with rectangles. Each level would take two contiguous rectangles and we lump them into a larger rectangle, and now we put a new level of clusters on that rectangle. Okay? And then we take these models into larger rectangles, and we do this in all possible ways until we get to a rectangle that's the whole image. Okay? So the depth of the network is actually not a parameter of the problem, it just falls out of how many pixels you have. Okay? The larger the image, the more depth you'll have. Okay? So numbers aside, here's an example of what happens that I think is, gives us some understanding of what we're doing here. So here are some of the original faces, okay? And here the problem is, to complete one side of the face given the other, right? this is not, you know, you could say, oh, you could do that by symmetry, right? We also complete the bottom half of the face given the top, but, you know, like, and planes and, you know, things like that that don't have symmetry. This is just so you can visualize what's going on. So if you look at it, the SPN is actually doing a pretty creditable job. So for example, you know, like this guy has a beard and the beard shows up over here. He has glasses, the glasses also show up, right? Maybe in a slightly fainter form. And also the SPN is a bit blocky, right? Because it's modeling things with rectangles. This is something that we're working on now, but you can see it's not perfect. But it's actually doing a reasonable job of reconstructing. Another notable thing is that, like, when you see a face at 3/4, right? The SPN actually understands that one side is supposed to be small and more hidden than the other. It just, you know, it doesn't make your face concave with two large sides and no small ones, for example. And the deep Postman machine, you know, again, we had a hard time getting it to work. Finally, we talked to Russell Akutinov, who's, you know, the DBM man, and he told us all these tricks. And we used those tricks. And finally, the deep Postman machine kind of worked. But if you look at what it's doing, it's really just doing a kind of nearest neighbor, right? It's taking a face and finding a similar face, but unfortunately, the similar face is not that similar. So no one could really call that, you know, a genuine image completion. The deep leaf network, we never got it to do anything useful, as you can tell. PCA, in squared area, was actually the second best, which is not surprising because PCA is explicitly minimizing the mean squared error, so that's what it's good for. But then when you look at what it's actually, you know, creating, like how is it filling in an image, of course, PCA, you know, it's a linear model. It doesn't understand anything about the structure of faces. All that you can do is form linear combinations of the data points, and that's what you actually have here. You have these ghostly superpositions of some set of faces that they found in the data were similar to those. Okay? So in terms of image completion, there's nothing very good going on. And with nearest neighbor, again, you know, the nearest face was not very similar at all, so nearest neighbor also didn't do very well. Okay. All right, so let's talk a little bit about structure learning. Most of deep learning, yeah.
So what happens if you take the pixel level representation and apply it to Cypher 10?
You mean like learn from Cypher 10?
Yeah, so like in Cypher 10 you have these like dictionary patches you're using for features. Could you use it like when you're reconstructing faces, you just get pixel features?
I mean, we could do this to Cypher 10. We didn't, but there's no reason why you couldn't. I mean, we did it for Caltech is a richer data set than Cypher 10.
It would be.
But yeah, I mean, we have the software available, you know, download and try it on Cypher 10 and thoughts about it.
So there's this like if it's comprehensible, then it would be interesting to see what the initial mixtures look like.
No, yeah, so we did that for things like, you know, Caltech 1.1 and Oliveri. And again, you can go to the SPN that we learned from the Oliveri set. It's like, oh, you know, here are some models of noses. You know, here are some models of left nostrils that are part of the larger models of noses. And these left nostrils go with those right nostrils and so on and so forth. Not all of it is this clear, but you can certainly, you know, you can zoom in and say, like, look at, because the SPN has this decomposable property and this fact that it's about, you know, it's a bunch of clusters, you can go in, you know, and see, like, well, what are you modeling? And show me what your model of that is.
Some of it's
Yeah, exactly. It's not completely interpretable, but it's, you know, but a lot of it is interpretable. So a lot of these networks are very, very large, right? And the likes of Google and Facebook spend enormous amounts of computing power computing these massively large networks. And in fact, talking with the people there, they say, like, we have a feeling that most of this structure is wasted. And, you know, we wish we could actually learn the structure of the network. So we actually did that for SPNs. There's actually, at this point, you know, there are dozens of algorithms for learning the structure of SPNs from various groups. What I'm going to show is just the simplest one, but I think it's a fairly old one at this point. But because it's so simple, I think it's a good illustration of how this can be done, you know, and of the power of SPNs. So here's how it works. Think of your data as a matrix of instances by variables. Okay, so each row in the training data is an instance, and each column is a variable. And so what we're going to have is a recursive algorithm that takes a matrix like this as an input. The top call takes as input the whole data, and then succeeding calls are going to take sub-matrices of that. Okay? And here's how it works. It's actually very intuitive. It's almost a one, the way the learning algorithm works is almost a one-to-one match with the definition of some product networks. In fact, when we were writing this paper, we wrote the abstract and we go like, wow, you know, everything there's to be said is already said in the abstract at some level, which doesn't usually happen. So here's how the algorithm works. When I'm given a matrix like this, the first thing that I try to do is break it up into subsets of independent columns. Right, using, you know, independence tests of one form or another. If I succeed in doing that, right, if I can break this up into subsets of approximately independent columns, and there's some kind of significance threshold or whatever to decide that, then what I can do is return the product of recursive calls on those subsets of variables. Okay? And if I'm able to keep on doing that successfully, I will eventually get to the point where I just have a single column, meaning I have one variable. And I can just model it with the univariate Gaussian or multinomial or whatever single variable model I want to use. Okay? Now, of course, typically, this is not going to happen because at least in the beginning, the variables aren't going to be independent because, you know, otherwise it would be an interesting problem. So what do I do in that case? In that case, what I'm going to do is I'm going to try to group the rows, the instances, into similar subsets. So what I do is I cluster the rows using, guess what, online hard EM, because we already had that, but you could do something else if you wanted to. And then what I return is a sum of recursive calls over those subsets of the rows. Okay? And the weights are just going to be the, for example, the weight of this guy is the fraction of instances that belong to it. Okay? So the weight learning just falls out of it. Okay? And typically what's going to happen is some alternation of these things until I finally get to this case. In general, right, it might be the case that I never find independent variables. If I never find independent variables, then what I do is I just keep doing this, right, until I have single rows. And then what this becomes is just a kernel density estimate. So this method for learning some product networks is very nicely kind of like the standard, you know, independence-based graphical model learning on one side, but also the kernel density estimate style of learning and the clustering EM mixture model type of learning on the other side. And it just, you know, weaves the two as dictated by the thing. How well does this do? We compared it with state-of-the-art Bayesian network and Markov random field learners. In particular, one of those was, you know, Microsoft's WinMind learner, which is, you know, the best Bayesian network learner in the world. It has, you know, bells and whistles that they spent many years adding. We used 20 varied real-world data sets for this, things like text data sets, you know, sensor networks, collaborative filtering, you know, basically all the things we could find that people had used before to test, you know, graphical models. They had between tens and thousands of variables and, you know, thousands and hundreds of thousands of samples, so, you know, fairly good size, not huge, but fairly good. And so what was the outcome? In terms of likelihood, it's a wash, which is actually what you'd expect. Sometimes the SPN achieves slightly better likelihood, sometimes the graphical models are slightly better, so, which corresponds to the fact that, you know, the SPNs model some things better and graphical models model some things better. But the big difference comes at query time. When you measure query accuracy, so like, you know, conditioning on these variables and, you know, we pick various random subsets, give me the probability, you know, the conditional probability of these variables, the probabilities that we get out of the SPN are much more accurate than the ones that we get out of the graphical models. Which illustrates this basic point that learning an accurate model is no use if the model is intractable, because then you lose that accuracy at inference time. In the case of the SPN, we don't have that problem. The inference is still completely accurate, so we get a very big win here. But the biggest difference is in the speed of inference. The speed of inference of the SPNs for all these data sets, for all these queries, was, you know, fractions of a second, and inference was exact. The speed of inference for Bayesian, you know, for the Bayesian and Markov networks, well, we tried various forms of MCMC and belief propagation. They were all slow, right? Sometimes the belief propagation just gave the wrong answer. The MCMC, you can just keep running it for more and more samples, right? And what we saw was, well, the accuracy gets slowly better, but if you had to extrapolate that curve until the accuracy reaches, you know, the accuracy of SPNs, you know, you'd probably be dead before it finished running. Okay, so finally, just a couple of interesting points that come out of this research. One is that the basic idea of some product networks is actually much more general than just building things like function approximators and probability estimators. The only properties that we use in defining an SPN are the properties of a semi-ring, in particular commutativity and distributivity. And as it turns out, many of the most studied and hardest problems in not just computer science but science all have the form of summing a function in a semi-ring. So for example, satisfiability, right? The semi-ring there is and or. The sum operation is or, and the product operation is and, right? And satisfiability is the or over the entire state. Okay? Integration is another example. Optimization is another example. Right? Optimization, basically what we have is the max sum semi-ring, because we're trying to maximize a function that is the sum of a number of terms. So what we did was we generalized the ideas in SPNs using the idea of a sum product function. A sum product function is any function over a semi-ring, using the sum of the product of the semi-ring. For example, another example is databases. Joins and unions form another semi-ring. So a lot of queries in databases also fall under this. And then we derive this theorem that is a sufficient condition for the inference to be tractable, right? So the inference in this problem is generally going to be intractable, NP complete or worse, like sharply complete. But what we've shown is that there's a single condition that guarantees tractability of the inference, that makes it possible to sum over all the exponential number of states in near time. And this is that the factors of each product have disjoint scopes. So every time you do a product, it has to be that the subtrees, right, the sum product function in general is a graph of sums of products. It has to be the case that the subtrees do not share variables. If the subtrees do not share variables, then the inference is tractable. In particular, for example, for the case of satisfiability, some product number is what is called a negation normal form, and this is a sufficient condition for satisfiability in N and F to be tractable. Okay? And that was this thing actually generalizes a lot of previous results that people had in individual semi-rings, that actually now that this is more general. And then we applied this. We've been applying this to a number of different things, but one thing that we applied it to was optimization, right? So optimization with the maximum semi-ring. If the objective function satisfies this theorem, then we're good. The inference is tractable. Of course, in general, the objective function will not satisfy that. It will be a sum of a bunch of terms that have a lot of overlaps in variables. So what we do is we approximate the objective function by a function that does have this property. So what we do is going to recursively build an SPN or an SPF, to be more precise, that approximates the objective function, and then once we have that approximation, the optimization is true. Okay? So we apply this to protein folding, which is a very hard optimization problem, also to structure from motion, and we just got results that were spectacularly better in the state of the art. So we were like several orders of magnitude faster to get the same quality of minimum as previous state-of-the-art methods. And the reason for that is that when we do this, the optimization, at least on a good day, becomes exponentially faster. Because whereas before I had, the problem with all these optimization models is that they have an exponential number of modes. There are the results of, I have a mode over these variables that interacts with another mode of those variables. The SPN decomposes the problem into its subproblems recursively, right? Some of the problems are decoupled, is that it just finds where the couplings are and then condition on the couplings successively, decompose them until you have easy problems. So whereas before you had to do an exponential amount of work, now you just have to do a linear amount of work, so you really can do much, much better. Okay, there are also some interesting similarities between some product networks and certain properties of the brain, right? So neural networks in deep learning are inspired by the brain, but inspired by one particular view of how the neuroscience works. Here's a different one. Right? This is very speculative, but I think it's interesting to think in those terms. There are two main types of cells in the cortex: pyramidal cells and stellate cells, and we can make a correspondence between pyramidal cells and product nodes on the one hand, and stellate cells and maximals on the other. Stellate cells are inhibitory cells. what a skeletal cell does is it takes a bunch of pyramidal cells and makes sure that, and it's a max selector. You make sure that the one that's firing strongest keeps firing and all the other ones die down. Okay? So you can think of a skeletal cell as doing a max. Okay? And you can think of a pyramidal cell, right? These are the new networks, the ones that typically appear in neural networks, as doing a product but in log space. Okay? So instead of doing a sum product, we can actually do a max sum, and that's what this is a max sum. Okay? So of course, this is a very different way to look at what's going on. It has some desirable properties. It also has some ways in which it's not, biologically realistic, or it's much more realistic than something like a Boltzmann machine. But maybe this is something that neuroscientists will find interesting. Okay, let me just summarize with the following observation. In AI and in computer science in general, there's always this trade-off between expressiveness and tractability. Okay? On the one hand, we like to have models that are highly expressive because we need them to solve AI problems, but then they're intractable. We can have models that are tractable, but at the cost of expressiveness. And graphical models are one, including deep Boltzmann machines and Markov random fields and so on, are one particular trade-off curve, right? And most of the research that we do on any given year is finding new trade-off points on this curve. Right? It's like, well, we're going to have this much less expressiveness for that more tractability and vice versa. But what we'd really like to have on a good day is not just finding a new point on an existing trade-off curve, but a whole new trade-off curve that's better than the old one at every point. Right? And this is what some product networks provide. Right? For the same level of expressiveness, some product networks have more tractability than graphical models. And for the same level of tractability, they have more expressiveness. And of course, there's still a whole spectrum of trade-offs that you could explore. And if you want to explore, you can go to this website, spn.cs.washington.edu, where most of the code that we've used is available. Also, data sets, pointers to papers from various groups on SPNs and so on, and we're continuously adding to it. Thank you.